to dive into extensible software. We're going to take a look at how recent changes in the way that we build and deliver apps has introduced some new challenges as to how we can provide extensions in today's multi-tenanted SaaS platforms. And then we're going to dive into how AWS Lambda has enabled the Forge team to build a secure platform for running third-party applications that enhances Atlassian's suite of cloud apps. Now, when Einstein said this, he certainly wasn't talking about extensible software. But we'll see that it's important as we explore the evolution of this kind of application. Now, when I look back at applications that truly benefited their customers, many of them were built in a way that enabled their end users to enhance the application to meet their specific needs. And these applications, they empowered their users to do this without needing to modify the core software at all. And many of these successful applications, they even went a step further and enabled the community to provide plugins via a marketplace, which enabled countless ways that the applications could be enriched. Now, how can an application like this change its spots? Well, there's a number of design patterns that we could draw upon to do this. Patterns like visitor and strategy and decorator and bridge could be used. And whilst we could dive into how you might use these to implement extensible code, instead, I'd like to touch on something else. You see, I've noticed that independent of how we implement extensibility, there's often a need for the extension code to coexist with the application. Perhaps you need to include the extension when you're compiling the code. Or maybe you dynamically load it at runtime, or throw it into the class path. However it happened, it usually required the code to be co-located, or at least very close to the application. And for those of you that built P2 plugins, I'm sure you'll be familiar with bundling the code into a jar file and shipping it to the class path of your end users, probably via the Atlassian marketplace. Now, don't get me wrong, I'm not trying to indicate that co-locating extension code is bad. I mean, there are a bucket load of advantages to co-locating after all. I mean, for starters, when the extension code is close, there's minimal performance penalty incurred when the core application needs to communicate with it. And often you can take advantage of things like shared libraries and reusing database connections. All in all, there's actually a number of strong advantages to co-locating. Each customer can run an independent install of their app, and the app can take on a slightly different shape. And each customer now can meet their individual needs and do this securely and safely. And this approach has worked really well for many years. But about 10 years ago, I believe the software industry reached an important tipping point that has changed the way that we build and deliver software. Now, as you know, transistor counts have continued to follow a Moore's law trajectory, probably doubling around every 2 years or so. And in the last decade, this count has crossed into the billions. Even the humble mobile phone has started to get microprocessors with over 1 billion transistors. However, interestingly, when you look at the rate of increase in clock frequencies, this increase has slowed significantly. Now, this is partly thanks to some small snags in physics, but all those billions of transistors, they didn't just get thrown into bigger caches. Instead, chip manufacturers have been embedding multiple processing cores, which has led to almost every new CPU in the last decade to be delivered with multiple cores embedded. And for us in the software industry, this is really important because it's enabled software running on these modern chips to utilize more parallelism over concurrency. And this has unlocked other complex components to become more efficient, including things like networking hardware and the software that supports it. And this has helped drive reduced network latencies It's improved internet speeds and provided greater availability of bandwidth. Also during this period, those bulky interchange formats like XML and SOAP, they were almost entirely replaced by the much more efficient formats like JSON and protobuf. And so all of this has culminated in the penalty of serialization and networking no longer being as significant a burden as it once was. And what I've observed from this is two major shifts in the way that we both build and deliver software. Firstly, it's enabled a move from applications that need to run locally or close to the end user towards being delivered online as a service instead. And it's enabled applications to be broken apart into smaller discrete services that continue to work together, but now cooperating over a network rather than as part of a single application. Now, how is this significant for extensible apps? Well, it's significant because it changes the way that the core application interacts with this extension code. You see, with both these changes, the extension can no longer be co-located with the core application. With the application broken down into microservices, the extension code is no longer just a method call away. Instead, extensions now need to provide a network serialized API that can be used by these discrete services to invoke the extension code as they need. And with the advent of these applications being delivered online as a service, these services now will often also serve multiple customers or tenants from within the same environment. And with this comes a perilous problem. You see, let's say customer one wants to enable an extension within this environment. Whilst customer one might trust the extension code, it cannot be assumed that customer two will. And nor can you assume that they would wish to operate it directly within this environment. And so it means that if the core application is going to be delivered as part of a multi-tenanted service, the extension code can now not easily operate within that environment. And now we need to ensure that any extension code that is enabled is not only enabled solely for the customers that wish to use it, but also that is completely isolated from every customer who doesn't wish to use it. So what's the solution to this problem? Well, one option might be to host the extension code externally. The core application could reach out over the internet to the extension code, and the extension code now is completely isolated from the application's environment. Now, this sounds pretty easy, right? And so whilst this might solve the problem, the extension providers now are no longer focused just on their business logic. Now, instead, as an extension provider, you're also taking on the burden of hosting it. How are you going to keep it secure? How will it scale with load? What about performance, resilience, operations? This is a lot of additional work. And this is where Atlassian's Forge platform comes into the picture. You see, the Forge platform allows you to go back to focusing on the business logic of your application, rather than all the heavy lifting that comes with hosting it. And now I'm sure at this point you're thinking, hold on, if Atlassian are operating a single platform with tens of thousands of applications, with each app on the platform not trusting the code of any other app on the platform, haven't we gone back to the same problem as before? What is it that has enabled Atlassian to host this single platform? Well, they did this by building the platform on top of AWS Lambda. AWS Lambda enabled Atlassian to provide a platform with all the necessary security and isolation capabilities they need to provide strong isolation between each Forge application and even between customers using the same Forge application. Now, what are these capabilities? Well, let's dive into how AWS Lambda provides these. And to do this, we're going to go right to the very bottom. You see, AWS Lambda is built on top of EC2. And so let's start with a typical EC2 metal server, something like an M5 metal. Now, one of these servers has 48 cores and almost 400 gigs of RAM. Now, that's more than enough hardware to potentially run hundreds of Forge applications, all from this one server. Now, of course, if we were to do this, we would certainly need to do this securely. We'd want to put in place protections to keep each app isolated from each other. And so what we're going to do is we're going to walk up the stack from this server all the way up to your Forge application, and we're going to look at the various layers of protection that are in place to keep each invoke of your app safe. So on this machine, we run Amazon Linux, and this is the host machine's operating system. And within this host OS, for each invoke of each Forge application, which is simply an AWS Lambda function, we're going to run a dedicated Firecracker process. Now, Firecracker is an open source virtual machine monitor. It's a virtualization manager that's been purpose-built for managing short-lived VMs, especially within a multi-tenanted environment. Now, I'm not going to dive too deeply into how Firecracker works, but if you are interested, it is open source, and you can dive into all the nitty-gritty here at this address here. But at a high level, Firecracker makes use of the kernel-based virtual machine module in the Linux kernel, or KVM as it's more commonly known. And it uses this to apportion some of the host machine's hardware to build a micro-sized VM. So you can think of these as things like CPU cores and memory pages. And so in the case of the Forge platform, what this means is for each Forge application, each time it's invoked, there's going to be a dedicated Firecracker process that's going to ensure that there's a dedicated micro virtual machine dedicated to that single invoke of the Forge application. That's right, an entire virtual machine for each invoke of your Forge application. And now within the micro VM is another Linux operating system with its own kernel, and we'll call this the guest. And so when Firecracker configures KVM to apportion some of the host hardware, KVM is going to do this by providing the guest kernel with an interface to some low-level features in the host. And these are things like page faults and registers. And Firecracker is also going to provide some virtual I/O devices to enable network and disk access for the guest, which you can really just think of as being an SSD and a NIC for the guest. And you might be concerned by those direct interfaces into the host. But from the perspective of the guest kernel, it only sees a view of the host world that's been presented to it. It doesn't have any mechanisms to view outside of this. Let me show you an example to demonstrate. Let's say we were to allocate 1 GB of memory to the guest VM. Now, KVM in the host kernel, which you can think of as being like a regular Linux process in some way, will malloc 1 GB of virtual memory space. And let's say it allocated these pages in the host. This memory area is going to be presented to the guest, and the guest will see this set of memory pages as its entire physical memory space. And now, let's say that the guest kernel attempts to access memory at address 0. What it's going to see is the first page that was allocated by the malloc, and not 0 on the host. And if, say, the guest kernel somehow was induced to attempt to access an address outside of its memory space, which would be outside of the malloc allocation from the host, well, this is going to be blocked by the host kernel. And this is just an example of how the virtual machine boundary using mechanisms like this, can provide a very strong perimeter of isolation. Let's continue our journey up the stack towards the Forge app. We're going to add a few more layers of protection along the way. And the next layer, it concerns the Firecracker process itself. You see, once the VM's up and running, there's actually very little that the Firecracker process needs to do. Now, most of its work is actually just processing the network and disk I/O from the guest. And so it actually has very little need for much of the landscape of syscalls that are available in the host. And for this reason, we can run the Firecracker process within a very restricted sandbox, which is created by a process that we call the jailer. And whilst the jailer needs to start with some elevated privileges, which it uses to set up the restricted environment, it can then drop its privileges and launch Firecracker as an unprivileged process in this environment. Cut off from much of the disk and almost all the surface area of the host kernel, and with very limited access to resources. And so now, if a malicious actor running on the guest could get past the guest kernel and past the virtual machine boundary, and somehow run some code within the Firecracker process, even then, it will only have access to a very restricted set of capabilities in the host. Okay, let's continue up the stack and take a look at the guest operating system. Within the guest, we use a similar set of kernel features to the jailer to build up another restricted sandbox, but this time within the guest. And so processes within the sandbox, they're going to be running within a Linux namespace. And thanks to some kernel features like cgroups and setcomp, we can place a number of restrictions on the kernel functions that are available and the resources that they can consume. And it's within this sandbox that your Forge application's code is ultimately going to be running. And so we've restricted access to the kernel, and with restricted visibility, and with limited access to resources within the guest, it makes it significantly more difficult for a rogue process running within the sandbox to successfully escape now not only the bounds of the soundbox, but then to also subsequently escape the bounds of the guest VM itself. Okay, let's add one more layer of protection. And this layer is actually provided by Atlassian. Now, within the guest sandbox, there's two sets of processes that run. There's AWS Lambda extensions, and any of these processes will be owned by Atlassian. They do operate apart from your Forge application, but they will be running within the same Linux namespace. So technically, you will be able to see them, but you can basically just ignore them. And there's a runtime, which is responsible for hosting and launching the Forge application's code. And this runtime forms the final protective layer. And for this, Atlassian uses a customized build of the V8 JavaScript engine. And your application code is going to be invoked within a V8 isolate. And you can think of an isolate as really just being a controlled JavaScript execution environment. And today, I'm going to show you just 3 of the techniques that Atlassian uses to restrict what Forge applications can do from within this execution environment. Firstly, any functionality that's not been implemented by the runtime is therefore not available to the JavaScript environment to use. And so by restricting the set of provided functionality, apps can now be limited in their capabilities. And so, for example, if the implementation of the file system module is not provided, then this code that you see here is simply going to fail. The Forge runtime also provides a custom implementation of node fetch, which is an important mechanism to enable you to make requests to external sites. However, this implementation restricts where requests can be made to only being the Atlassian APIs and the sites that have been allowed by both your app's manifest and by your customers. And so an attempt to access a domain that hasn't been approved by the customer site is also going to fail. And finally, a third technique that I'd like to show you is the use of V8 isolate snapshots to aid in the prevention of accidental cross-tenant data leakage. Now, something I haven't mentioned yet is that AWS Lambda can reuse the micro VMs that it sets up for a specific Lambda function, or Forge application in this case. And so what it means is that if a VM is reused, the runtime process will be paused and then resumed. And we do this because it's an important performance enabler, as the VM then doesn't need to be recreated for each invoke, and the runtime won't need to be initialized again. However, in the case of Forge, this introduces a potential for accidental cross-tenant data leakage, as static variables now are going to live on between invokes. And so to guard against this, when a Forge application is invoked, the application code is actually executed from a snapshot of an isolated environment that was taken when the function code was first submitted. And this is long before any customer-related invoke has occurred. And what it means is that when the VM is reused, code like this, which could have resulted in an accidental cross-tenant data leakage, would in fact not result in any leakage across the tenant boundary at all. And so there we have it, 4 protective layers that build upon each other to provide strong isolation for your Forge application code. And not only from other Forge applications running on the platform, but also from each individual invoke of your Forge application. And so now, thanks to the solid foundation provided by AWS Lambda and the Atlassian Forge platform, you can now go back to focusing on the core business logic that your application provides to Atlassian's customers, and you can leave the heavy lifting in the hands of Atlassian and AWS. Thank you.